I'm ready. Now that I know we don't start.
All right, this is the last cranial nerves of the brainstem. 1 and 2 aren't really going to hit there. We'll cover them in the next unit. So today is about 3, 4, and 6. Do you notice anything strange here? A little jerky. Yeah, this is supposed to be smooth pursuit. But you see that some saccades are coming in. Any damage in the brainstem nuclei we're going to talk about today, the cerebellum, cortical, subcortical structures as well, can impair eye movement. This is most likely caused by damage in the brainstem or the cerebellum. You can see deficits with smooth pursuit here. Inappropriate saccades. So those are the two types of eye movements that we can have. The saccades would be the fast, ballistic movements of the eye from one location to the other rapidly. And the smooth pursuit would be that smooth, graded movement from left to right or up to down. Smooth pursuit is only going to be initiated whenever we're tracking an object. And we could track it because it's moving, or we could track it because our head is moving. Either way, it's changing its position relative to where our eyes were pointed the moment before. Whether it's moving or we are moving, doesn't matter. It's still changing its location in our visual field, and we're trying to keep it in the same spot. So this smooth pursuit is essentially error detection and correction. If this object that I'm looking at doesn't stay in the center of my visual field, fix the error. And that fix is going to happen moment to moment, and we need very fine movement of the eyes. Luckily, we have non-twitch muscles in our eyes. I think these are the only non-twitch muscles that exist in our bodies. I could be wrong there. I don't know a whole lot about muscles. So ask someone else, see what they say. But non-twitch muscles are going to help us get those smooth movements that we can see in between the saccades. The saccades are your straightforward fast twitch. Twitch here meaning the firing of action potentials, as we'll see. There's really two things to talk about with the eyes. Moving them, so the extraocular muscles, how we control them. And then the intraocular muscles. So the autonomic input, changing the size of your pupil, changing the thickness of your lens, things that we'll need to do still in order to see. So we have to point our eyes in the correct direction, and we have to make sure that we have enough light and that the object we care about is in focus. The first thing we'll talk about is how we actually control the movement of the eyes. 3 cranial nerves here, the third one is the major one. These other 2 are only going to control single muscles, but since there's only 6 here, one muscle is still pretty substantial. So your abducens and your trochlear nerve, single muscles there. The abducens is going to abduct the eyes. The trochlear nerve is going to be more involved with rotating the eyes or moving it downward, depending on the angle, as we'll see, because we're innervating the superior oblique here, which is going to actually wrap around this trochlea, this little bit of cartilage. Here's all the cartilage in your orbit. It makes essentially a little pulley that this muscle wraps through. So here's a little tendon there wrapping around, making an angle, so that the oblique muscles, whether it's superior or the inferior down here, will wrap around. They're going to hit the eye at a different angle than your rectus. This is going to allow our eyes to move up and down depending on their angle, because it will move our eyes around depending on the way that our eyes are pointed. These different muscles will have different effects on its position. For example, when we're looking straight ahead or maybe a little adducted, this superior rectus is going to turn our eye upward because the eye will be in the same plane as the muscle. As the eye turns, as it tends to do throughout the day, it's going to be at a different angle to the muscle. And so when we contract the superior rectus, if our eye is facing this way, like it is, if you just imagine, use your imaginations here. We all have those. So whenever we turn inward there, when I'm looking to the right, took me a while there, this contraction is going to instead rotate the eye. And you'll need that because you'll notice when you're looking straight ahead, we're not dead on with the plane of any of these muscles. So when I contract my superior rectus, yeah, I'll turn the eye up, but I'm also going to rotate it. I'll rotate the top inward. So I'll get a little intorsion of the eye. And I need to correct that so I'm not twisting my eye. So I can just look up and everything stays horizontal. It's horizontal. I'm not twisting the world too. So we'll use our inferior oblique to help correct that rotation. So all these muscles are going to be working together to move our eyes about because we need very fine control over eye position. Small changes produce large changes in your visual field. It doesn't take much of a turn for me to look at a completely different part of the room. So if I can't put my eyes where I want them, I'm going to have a difficult time seeing. So these 6 muscles here, most of which are going to be controlled by the ocular motor nerve, are going to move our eyes up, down, left, right, and then rotate them accordingly. Because our head will move too, a little bit throughout the day. And we'll actually rotate our eyes with subtle head movements to prevent shaking of our visual field. So it helps essentially, not autofocus, what do they call that, where you take a recording and the little jitters get corrected out. There you go, yeah. So we have that built in. We've had that technology for a long time now. Our phones have it too. It'll cut down on your visual field in the video there, but it helps the video look a little bit smoother. That's what our eyes are doing as well. So they'll rotate as our head rotates a bit to make sure up stays up. Of course, big changes, those aren't going to get canceled out. But the little subtle changes in head movement are going to get canceled out. And any of the twisting that occurs because we're off plane with the muscles, those will get canceled out as well. So by having these muscles hit at different angles, whether it's the superior rectus in this case or the superior oblique, they're about 90 degrees to one another. That means you can turn your eyes up whether they're facing this way, that way, or anywhere in between. The ocular motor nerve is going to have a few other things that it does for us. It's going to help keep our eyelids elevated, so provide some tonic excitation there, so to keep our eyelids open. It's also going to provide the parasympathetic input that we're going to talk about in the next part here. So the third cranial nerve there is a major one for the eyes. When it's damaged, you'll tend to see the eyelid closed. There'll be severe deficits in the movement of that eye, and the ability of the pupil to change its size will be impaired. But of course the eyelid's closed, so that probably doesn't matter that much. So we're going to hit some extraocular muscles to move the eyes around. We'll also keep our eyelids open. The types of muscles that we find in each of these come in 2 types. We have our fast twitch, which are very similar to what you've learned about for any other fast twitch. They're going to fire action potentials. Here we can see an action potential being fired. In this muscle fiber, not so much. You stimulate the nerve, and you see instead this little tiny depolarization. No action potential. This is a non-twitch fiber. Rather than firing action potentials, they just have these gradations in membrane potential change. That depolarization is not going to spread throughout it, so the pattern of synapses that you see on these muscles is different from the fast twitch fibers. These are going to form your pretty typical single neuromuscular junction, just like on the rest of our skeletal muscles. On the non-twitch fibers, we find it looks like little grapes, hence the name. So you'll find multiple little synapses along the way. They'll sometimes be called multiply innervated muscles. So there's two synapses that they'll form here. There's the little grapes on the vine along the way, and then there's these endings. These are called palisade endings, and these are going to allow for fine adjustments. It'll make a little more sense when we look at the cartoon here. So here's a little extraocular muscle here. We have our fast twitch fibers. They get the nice single neuromuscular junction. They'll fire an action potential. So depolarization here is going to spread throughout the muscle, allowing for uniform contraction. These non-twitch fibers don't fire action potentials. They get those gradations in depolarization, but they never actually fire an action potential. So the depolarization you get here spreads passively. It's not actively propagated throughout the entire muscle fiber. And that's why we're going to have multiple grapes along that vine, because each of these grapes is going to provide local depolarization. So we get very weak, smooth contraction, very fast contraction. So these fast twitch fibers are going to be useful for saccades. We're getting rapid, uniform contraction and rapid ballistic movement of the eyes. Those slow, graded movements of the eyes, that's going to require these non-twitch fibers. Rather than having the entire fiber contract all at once, small portions can contract, and we can make fine adjustments out here at the end where it connects to the tendon. So we form multiple synapses. Only at those areas are we going to have depolarization. It won't spread throughout the entire length, and that's going to allow for more subtle changes in muscle length. The whole thing doesn't contract at once. It's unable to propagate that depolarization away from the synapse like these fast twitch fibers. The twitch in this case being that action potential. So you only have to depolarize here, and everywhere else depolarizes. We get calcium throughout. Actin myosin interact with one another, shorten your sarcomeres, the whole thing shortens. When you can't fire an action potential, you're only depolarized where you're getting acetylcholine release. So smoother contraction there. The control of these muscles, of course, comes from the 3 cranial nerves, and those are going to be controlled by central pattern generators that we call gaze centers. These 4 centers control the direction of our gaze. Left, right, up, down. We have 4 gaze centers. 2 of them are concerned with left or right. So there's a left paramedian pontine reticular formation. When that's active, we look to the left. When the right paramedian pontine reticular formation is active, we look to the right. Nothing tricky there. The name tells you where it is. It's around the middle of the pons. There it is right there. Here's your pons. Right around the middle. Close to the abducens nucleus. That cranial nerve that's only concerned with left-right. That's all it does. It does no up-down. It's left-right. So that makes good sense. The third cranial nerve, which is concerned with pretty much everything, is going to be much closer to the up-down gaze centers. These have a couple different names. One is pretty terrible, the rostral interstitial nucleus of the medial longitudinal fasciculus. There's also the thalamo-mesencephalic junction, TMJ. You can use whichever you like. I have my thoughts on which one that's going to be. So the dorsal TMJ, that's going to allow us to look up. Dorsal is above ventral. That makes sense because the ventral one is our down gaze center. So the more ventral portions of the thalamic mesencephalic junction, in other words, between the thalamus and the midbrain. The midbrain is where we find the oculomotor nucleus. Right there, the dorsal portions make us look up, the ventral portions make us look down. So here's your D-pad. This will determine which way you're looking. It's going to take input from the cortex, sending input from the brainstem, and it'll convert that into a pattern of output that moves your eyes in the appropriate direction. So your cranial nerve nuclei don't have to really think about anything. You don't have to think about all the fine details. You just think, I want to look left, and the central pattern generators figure it out. How can I accomplish that left gaze? Well, of course, they're going to use a few different neurons to accomplish this. So the circuitry that you're going to find in here, there's 2 types of output neurons. Tonic and burst. These are going to control the activity of the lower motor neurons that then innervate those muscle fibers. So the lower motor neurons in cranial nerves 3, 4, and 6 are going to get input from tonic and burst neurons. Both are excitatory. So we're dumping glutamate here. Tonic, exactly what it sounds like. Tonic excitation, muscle tone. They're going to hold your eyes still. Depending on their firing rate, that's going to determine the length of the muscle. Increase the tonic firing rate, increase the amount of acetylcholine you're releasing, increase the contraction. So shorten the length of the muscle, and vice versa. Slow these down, lengthen the muscle. The burst neurons are there to allow rapid contraction, quick changes, saccades, as you might imagine. Here we're looking at the activity of a motor neuron relative to the eye position here. So we're changing the angle of the eye and holding it still. You'll notice there's a slight change in tonic neuron output because we're changing the length of muscles in order to change the position of our eye. If I want to look right, my medial rectus is going to need to shorten over here. The lateral rectus needs to lengthen, and vice versa over here. During that movement, we get a burst of output so that we have rapid contraction of the muscles. So we have saccadic movements, and that's going to be accomplished by burst neuron. You sum these together, you get this. So both of our excitatory neurons here are going to control motor neurons. One's more involved with tonic position, muscle tone. You could slowly increase the activity of the motor neuron here, or you could rapidly increase its activity to get a saccade. These burst neurons are controlled by omnipause neurons. These are most likely glycinergic neurons because they're in the brainstem. What these do is inhibit burst neurons to prevent inappropriate saccades until we have chosen to move our eyes. When we make that choice to move our eyes, descending cortical input inhibits the omnipause neurons. There's your inhibition. There's your decision to move your eyes. When we inhibit the omnipause neuron, we stop inhibiting the burst neurons. So they fire a burst. When they fire a burst, motor neurons fire a burst, and our eye position changes. And of course, there's going to be some inhibitory interneurons linking together our two gaze centers. If you're trying to look left, don't try to look right. If you're trying to look up, don't try to look down. So these two sides will inhibit each other. Yeah?
So what inhibits omnipause neurons?
Your descending input. Yeah, so from the cortex or the superior colliculus more directly, your decision to move your eyes. What allows us to make that rapid eye movement is the pause of inhibition from omnipause neurons. So burst neurons fire. Those burst neurons are going to provide strong excitatory input then to the lower motor neurons, and we contract. Of course, the other side is going to be inhibited. So the left gaze center here is going to be acting on two muscles. So there's our lateral rectus on the left and the medial rectus. From the left eye left and the right eye left. These are connected to one another. There's actually a pathway from the abducens nucleus to the oculomotor nucleus. The more medial portions of the oculomotor nucleus are going to innervate the medial rectus. This connection here is kind of nice because anytime the abducens is active, the contralateral medial oculomotor nucleus is also active. Meaning, if I look left in my left eye, I look left in my right eye. Alternatively, if I'm looking right in my right eye, I'll look right in my left eye. So they'll move together. This gives you your left-right coordination. What contributes to that as well would be inhibition from these gaze centers. So that when one side is active, it stimulates the appropriate lower motor neurons to then contract these two muscles. At the same time, we're inhibiting this side, which would try to contract the antagonist. So whenever we stimulate the left lateral rectus, we're always going to inhibit the left medial rectus while activating the right medial rectus. This way you have left-right coordination. And they're not going to fight each other. Of course, that's not always the case. You can cross your eyes. You can converge your eyes. There's going to be other neurons down here that create a different pattern. They're called divergent cells, as we'll find out, and they'll project bilaterally up to the medial portion of the oculomotor nucleus. So both medial recti are going to contract, and you'll cross your eyes. The control of these gaze centers comes from a couple sources. So the vestibular system can control our gaze centers. So we get smooth pursuit, essentially. Rather than the object moving, our head moves. So you can keep your gaze fixed on whatever you're looking at as your head changes position. It's still smooth pursuit, just from a different angle. We, of course, sense that head position. We're going to sense any change in head position with the semicircular canals. So as we look to the right in this case, the right lateral duct is going to be stimulated. That vestibular nucleus here is going to activate the contralateral left gaze center, so the left paramedian pontine reticular formation. That gaze center is just a central pattern generator. Whenever it receives input from the right medial vestibular nucleus there, it translates that into left gaze. At the same time, it inhibits the opposite paramedian pontine reticular formation. But that's not excited anyway. That right turn decreases the activity on the left side, so reduced excitatory input, increased inhibitory input. We are not going to look to the right, we are only going to look to the left. And the gaze center figures all that out. We can, of course, control where we're pointing our eyes. We can choose to look around. When we do that, it's going to be a saccade. You'll only get smooth pursuit if you're looking at an object. It's the only way to get it. And this has to do with the circuitry from our cortex to the gaze centers. They're going to be acting more on those omnipause neurons. So we're going to get bursts. And those bursts are going to create saccades. There are a few what we call eye fields. These are portions of the cortex that correspond to movement of the eyes. And they'll involve different types of information. Your supplementary eye field, for example, deals with learned movements. How you should move your eyes if you want an object, let's say here, I'm gazing here. If it's this far off and about some distance from me that I've guessed based on blurriness, the difference in my two eyes, I know I need to turn my eyes that much. Got it. We learn how to control our eyes and we store that here. So this is going to help tell the frontal eye field, this is our ultimate output. The frontal eye field is going to know how to move the eyes based on how have I moved them in the past to accomplish this, and where's the stuff that I care about. So in the parietal eye fields, this is more with object tracking. I really want to look at that skeleton. I know it's over there. So I look. I know how to turn my eyes that way, and I know where the skeleton is relative to the center of my visual field. Then I get a quick burst, because my frontal eye field is going to stimulate the superior colliculus, which then is going to go down and inhibit the appropriate omnipause neurons. At the same time, we're going to go through the basal ganglia here. We're going to inhibit the substantia nigra, pars reticulata, which normally inhibits the superior colliculus. So this prevents saccades. Whenever you want to suppress saccades and have smooth movements, there's a number of structures that are going to do that. One of them is the substantia nigra. Have we heard of the substantia nigra before? Great. When did that come up? Parkinson's. Great. So neurons in the substantia nigra are going to die from Parkinson's disease. Mostly it's the dopaminergic neurons, but you'll see cell death in other populations as well. For left-right gaze, saccadic movements are going to be contralateral. So if I want to look to the right, if I want to stimulate my right gaze center, it's all over here on my left. If I want to look left, it's the right. there's just a single cross. We're going to get a double cross down here for smooth pursuit. So slightly different circuitry here. We'll still invoke the frontal eye field to some degree because it's going to know where objects are. It's going to have some idea of learned movements. But really what we're talking about here for smooth pursuit are going to be regions of the cortex that are more closely innervated by the visual cortex down here. So in the occipital lobe, in the back of your head, that's your visual cortex, as we'll find out later on in this class. Right there at the junction between your parietal, occipital, and temporal lobes there, we have an eye field that's going to be more concerned with object tracking. The temporal lobe is going to help remember where things are. This, of course, will tell you exactly where things are. The parietal lobe will help figure out spatial relationships between different objects. So together, we're going to have an idea of where something is right now relative to our center of the visual field. Any deviation from that is an error that we then correct. We're going to be correcting these errors down in the brainstem. So we'll go down to the pons and into the cerebellum. Here's where we cross over once. So we go into the cerebellum. We're going to be hitting that flocculonodular lobe, so we get direct output to the vestibular nuclei, essentially hijacking the vestibulo-ocular reflex. Because you'll notice that's smooth pursuit. That's smooth pursuit. It's the same movement, but rather than movement of your head and activity in these semicircular canals driving this, now it's just, where's that object relative to the center of my visual field? If it's not right in the center, make it there. If it's moving to the right, immediately correct that. Just like if my head is moving to the right, correct that. So we're just correcting the error here, just like we are with the vestibulo-ocular reflex. Rather than driving it by head movement, it's driven by object movement. But either way, our gaze stays fixed and we have smooth pursuit, not saccades here. We're not invoking the superior colliculus and those omnipause neurons. Yeah.
So if it's error detection, is the inferior olive involved in this?
I don't think so. Not in this case, no.
Because it's movement, it's like rotors.
If you have an inappropriate movement, yes. So there are cases where you can give someone special glasses so that it changes the amount of eye movement needed to actually keep that object in the center of the visual field, and they'll learn that new amount of movement. So there can be that, but only if there's an actual error in your movement relative to what you wanted. The error detection is more up here. And that's the difference between where an object is and where it should be. It should be in the center of your visual field. As it moves, we move our eyes to keep it there. That's the correct thing to do. The error is in the object, not your movement. When the error is in your movement, though, yes, absolutely, inferior olive comes in and we can modify it so that there can be learning of this. We pick it up so early we don't realize it. But if you get some special glasses, you can relearn it. Sounds fun. Okay, so then from the vestibular nuclei there, we're going to cross right back. So it's the double cross. So ipsilateral in this case. So when I'm tracking an object, moving to the left, that's going to more involve the left side of my cortex there, and the right side for rightward movement. Slightly different circuitry. Both of them are going to affect gaze centers. One of them is going to cause the inhibition of omnipause neurons, a burst of excitation, and a saccade. The other is going to be more involved with fine changes in the tonic output. And that's going to be down here. And you'll notice we're involving a few more brain structures here, but everywhere along the way we've involved the cortex and the brainstem. So you can have damage anywhere in these pathways and get difficulties with eye movements. Damage to the frontal eye field, for example, is going to affect your initiation of saccades. They tend to occur a little bit later. If damage occurs there as well as the superior colliculus, no more saccades. So you can't initiate saccades anymore. Of course, if you have damage to those cranial nerves that innervate your extraocular muscles, you'll have the appropriate weakness or paralysis. Same thing for gaze centers. So if we're unable to excite the lower motor neurons, of course, they're not going to excite the muscles either. Damage to the vestibular system can, of course, impair this. I just want to bring the basal ganglia into this, since we haven't touched on this yet, but we will. So whenever we have degenerative disorders that affect the basal ganglia, like Parkinson's disease, we can have difficulties with eye movements. Recall here that the substantia nigra is inhibiting our saccade machinery there. So whenever you have degeneration of those neurons, you get inappropriate saccades. So we're looking at smooth pursuit here. They're just tracking eye position. Here's an age match control. So they're just going back and forth. You should see this nice sinusoidal pattern of left, right, back and forth. So pretty good at object tracking. It's showing you a dotted line here and here where the object is. You can't see it in the control because they tracked it appropriately. In the PD patient, that left-right tracking gets interrupted by these saccades. So you see these rapid deviations away from where their eyes should be, where the object is. Left, right, left, right, left, right. As they're moving along, they get saccades when they didn't want them because they've lost neurons right here. So now they have a difficulty with inhibiting saccades, so that whenever we're trying to carry out smooth pursuit, the frontal eye fields can inappropriately initiate saccades. So when we're thinking, I want to keep tracking this to the left, we get a saccade. Damage to the cerebellum can cause a variety of dysfunction with eye movements. Of course, they're going to play a role in carrying out smooth pursuit as well as suppressing smooth pursuit whenever we want saccades. So you can see a variety of things with cerebellar damage. Here we're looking at saccades. So quick, left, right, and here's the smooth pursuit. So you can see some inappropriate saccades here. The timing isn't quite right. They never really quite match up. They can't track the object well. The cerebellum is central to smooth pursuit. As you can see here, they fail to track it at pretty much every step. They never quite catch up. They have inappropriate saccades, and their timing is just off. As it will be with other muscles, the timing of their extraocular muscles never quite matches up. They're a little late to the ball game here. You just can't quite keep up with it. The amount of movement is never quite appropriate. Here you can see a little dysmetria there. Okay, any questions? All right, let's talk about these then. Well, let's talk about autonomic input to the eyes then. What we're going to be controlling is how much light we allow in, so size of the pupil, and where that light hits. How far back or forward is it going to hit? We're going to adjust the thickness of the lens so close objects can be in focus, and we can focus on more distal objects as well. This is, of course, going to be based on sensory input. How much vergence is there in my eyes? That's how I determine object distance. When my eyes are closer together, I know I'm looking at something closer than when they're looking at something further away. They'll diverge a bit so that the one thing I'm looking at is in the center of my visual field of both eyes. That vergence is going to do a couple of different things. It's going to change the thickness of my lens and the size of my pupil. So there's a couple reflexes here. They're both going to involve the third cranial nerve. That's what's going to provide our parasympathetic input. So the first reflex is the pupillary light reflex. Regardless of ambient light levels, we're going to make sure there's enough on the retina. Not too much, not too little. We want the Goldilocks range here. And we're going to control how much light goes in by adjusting the size of the pupil. Make it bigger, more light comes in. When you go outside and it's bright, you constrict your pupil, less light gets in, you're not going to overwhelm your retina. Because we want to have contrast between the different shades. And if you're overwhelming your retina with light, everything looks white, it kind of hurts. So this reflex is going to allow us to make sure there's enough light regardless of ambient light conditions. So we have to have a light sensor, of course. If we're going to adjust pupil size based on light, we have to be able to sense light. That's not too difficult, we're in the eyes. It's a little different than how we'll sense light for vision. This is closer to how we sense light for circadian rhythms. Retinal ganglion cells, which create the optic nerve, some of them have light sensing photoreceptors. Normally, retinal ganglion cells get input from photoreceptors via bipolar cells. We'll cover this later. But they don't actually sense light directly, except for this special case here. Those retinal ganglion cells are going to project to the midbrain or to the hypothalamus. Those directly sense light. And rather than projecting back to the medial geniculate nucleus and then the visual cortex to create some visual perception, they instead are involved with more reflexive behaviors, whether it's your moment-to-moment pupil size or light entrainment, circadian rhythm generation. Same thing, we have specialized retinal ganglion cells. That's what RGC means here. So down there in the, well, not quite the very back, that's where our photoreceptors are, but a little in front of them, we have these retinal ganglion cells that sense light. They project back to the midbrain, to the pretectal nucleus. So here's our secondary afferent in this case. So here's our second neuron. The pretectal nucleus is then going to excite bilaterally the Edinger-Westphal nucleus. Here's our preganglionic parasympathetic neurons. So here's neuron number 1 for output. Then there will be neuron number 2 for output. So 2 to go in, 2 to go out. Number 1 for input is in the retina. Number 2 is in the pretectal nucleus. The preganglionic parasympathetic neurons in the Edinger-Westphal nucleus then project to the ciliary ganglion, and the post-ganglionic neurons there are going to innervate the iris. They will cause constriction when there's an increase in light. So increase in light, stimulate your retinal ganglion cell, stimulate your pretectal nucleus, stimulate your Edinger-Westphal nucleus, stimulate the ciliary ganglion, stimulate smooth muscle here via muscarinic acetylcholine receptors. This is still parasympathetic. And 3, meaning it's GQ. GQ is going to increase calcium. That's going to be excitatory no matter what kind of muscle cell you are. So the smooth muscles in this case constrict. And here we're talking about the sphincter pupillae. So just around the pupil there. When that round muscle constricts, the size of your pupil increases. And we let in a little less light. Let in a little less light. Decrease activation here, decrease activation here, decrease parasympathetic output. So this will allow us to get just enough light. How much is enough? Whatever it takes to stimulate our retinal ganglion cells enough, but not too much or too little. Stimulate them beyond what they want, constriction. Don't stimulate them enough. Well, then we don't get parasympathetic input and we have relaxation. So our pupils open up. So this keeps a constant level of light on our retina. If it increases, pupil shrinks. If it decreases, pupil opens. And it's just 4 neurons involved there. 2 sensory, 2 for the parasympathetic input. Now you'll notice here we have bilateral input from the pretectal nucleus to the Edinger-Westphal nucleus. This is why shining light in one eye, which I won't do with this, is going to give you a consensual response. So the other eye will respond as well. Even though all the light's hitting here, both pupils are going to constrict because we have bilateral innervation of our preganglionic parasympathetic neurons. So regardless of which eye there's light in, they're going to work together. The accommodation reflex deals with eye adjustments that occur based on object location. If we're looking at something close versus far away, our eyes are going to converge or diverge a different amount, and that degree of convergence is related to closeness. The closer the object, the thicker your lens will need to be. The more distal the object, the thinner your lens. And this way we ensure that that object we want to look at is in focus on the retina. It's not being projected too far back or too far forward. So that comes in clear. All the stuff that's past what I'm looking at is a bit fuzzy, and there's two copies of it because my eyes aren't matching up. So whenever we look at something close, whenever we want to focus on something close to us, we can activate both oculomotor nerves and callus, the convergence of your eyes. So both medial rectus muscles are going to constrict and your eyes turn inward. When that happens, we also have a little parasympathetic input as well. So those virgin cells down in the reticular formation that are helping us look at something that's a bit closer are going to do two things. They're going to cause convergence of the eyes via the third cranial nerve, and also parasympathetic input, again, via the third cranial nerve. So when our eyes turn inward, because we're looking at something closer, we need to adjust the size of our lens. We'll also adjust the pupil as well. So this is going to allow us to be a little more selective on where the light is coming from. So when you constrict it, it's going to be a more focused beam of light coming in. You have a smaller hole to go through to get there. So the constriction is going to help us restrict the eye, the light that's coming into the eye, and the thickening of the lens will help us focus it. Here we're getting parasympathetic input onto these ciliary muscles off to the side. So there's one over here, and then we have some ligaments holding this crystalline lens here. The thickness of that lens depends on how hard we're pulling on it. It's going to depend on whether we're constricting our ciliary muscles or not. So whenever we constrict these, they'll shorten this way, lengthen out a bit, so the tension drops. We're not pulling on the lens as hard because we essentially just thicken up this ciliary muscle when it constricts. It's going to constrict, of course, from acetylcholine input acting on GQ-coupled M3 muscarinic receptors. So we excite the ciliary muscle. It shortens up this way, lengthens out here. We're not pulling on the lens as hard, and it thickens. That thickening is going to allow us to focus the light coming from closer objects. The stuff behind that is going to look a bit fuzzy. When you look at something a little more distal, your eyes aren't converging as much. Reduced parasympathetic input in that case. So rather than thickening the lens, we can thin it out. You can also, of course, thin it out with sympathetic input. Sympathetic input is going to arise from your thoracic spinal cord. It's going to ascend up to the superior cervical ganglion. Here's your post-ganglionic sympathetic neuron. That axon is going to enter the cranium by riding along the carotid artery there, and there it's going to form the ciliary nerve that innervates the eye there. And here's where we get our sympathetic input. So parasympathetic is all from the oculomotor nerve, third cranial nerve. The sympathetic input from the thoracic spinal cord is going to do just the opposite of what our parasympathetic does. So rather than constricting the pupil, we're going to dilate it. We're going to act on two targets there. So we're going to relax that pupillary sphincter, so the round muscle there. We're going to relax it, of course, via GS-coupled receptors. This is smooth muscle, remember. So when we activate protein kinase A, it prevents phosphorylation of myosin light chain. Myosin doesn't interact with actin. No constriction, instead we get relaxation. It's going to stimulate the more radial dilator pupillae muscles. Rather than being a circle, these are going to be fibers running out. When they constrict, they pull open the pupil. So we get dilation with sympathetic activation. We'll flatten our lens. I suppose the logic here is that there's some threat that we need to be on the lookout for. Hopefully it's not on us, eating us yet. So we relax our ciliary muscles. We can look a little more distally. That's the idea anyway. Again, these are GS coupled. Smooth muscle relaxes as a result. And we'll open our eyelids a bit more. So this is yet another way we can raise our eyelids. Here we're going to have GQ coupled, alpha 1 adrenergic receptors. So our eyelids raise. We make sure our eyes are open so we can look around for whatever the threat may be. We're going to focus on more distal objects and we'll let in plenty of light so we can see it. These are both going to act together, and you'll get subtle changes in the size of your pupils, lens thickness. Any questions? All right, let's go through these then.